In this video, we want to look at something called the empirical rule, outliers, and the z-score. Okay, so first, a mound-shaped distribution is any distribution that looks similar to one that I've drawn here. So whereas most of the data points are going to be clustered near the mean, very few data points will be extremely large or extremely small. So this data set represents heights of adult women, and you can see that most women are close to the mean height of about 5 feet 6. Nothing special about height. I could have had a distribution of SAT scores or blood pressure rates or lengths of pregnancies. And what we would see is a lot of variables in our everyday world follow this mound-shaped distribution. Most of us are average. Very few have exceedingly high or exceedingly low scores. Okay, so there's an important property that is useful for all mound-shaped distributions, and it's something called the empirical rule, and you want to remember this. So the empirical rule says anytime you have mound-shaped data, we know, it doesn't matter what the variable is, it doesn't matter what this is, if the data is mound-shaped, we have three properties. That if we mark the mean in the center and then add on one standard deviation and subtract off one standard deviation so we get this light green region, we know about 68% of our observations will fall in this range. So about 2/3 of your data are very close to the mean. Then if we go out another standard deviation in each direction, so this medium green and light green area, we know that about 95% of all observations will fall in here. And finally, if we go out 3 standard deviations on each side of the mean, nearly all of the data will fall in that range. And notice it's nearly all. Turns out that it's about 99.7% of data falls within 3 standard deviations. Okay, so again, doesn't matter which variable is, but we have this rule that you'll see sometimes referred to as the 68, 95, 99.7 rule because of these percentages. So you want to keep this in mind. Or smaller. Okay, so I'm telling you, math SAT scores are roughly mound-shaped. So I've traced out the general shape of what I expect SAT scores to be. And the mean is 500, so I'll go ahead and mark the mean of 500 here. And I'm also told the standard deviation is 50. So again, I'm going to mark a standard deviation, add 50 onto the mean, subtract off 50 from the mean to get 1 standard deviation from the mean. And then I'll go out 2 standard deviations from the mean. So I'll add another 50 to get 600. I'll subtract another 50 to get 400. And then I'll do this one more time. I'll go out a 3rd standard deviation. And we can use the empirical rule then tells us that nearly all of the math SAT scores, for instance, should fall between 350 and 650. 68% of them should come between 450 and 550, and 95% of them should fall between 400 and 600. So now, if we know someone's SAT score, we can see, do they seem close to the mean or far from the mean? Her score, unusual. Okay, and so I'll mark her score with a K, and she got a 540, and she is here. She's a little below 1 standard deviation from the mean. She's not unusual at all. She's in the middle of the pack. Is he unusual? And I'll mark this with a J, and now Jackson is more than 2 standard deviations, right, below the mean. And we know that 95% of the observations fall in here. So the other 5% fall here or here, and this graph is symmetrical. So half of 5 is 2%. So only 2.5% of people score out here. So Jackson's unusual. He's in the lowest 2.5% of. Again, Kia, just eyeballing it, is just under 1 standard deviation above the mean, where Jackson is more than 2.5 standard deviations below the mean. That seems reasonable. She is not quite 1 standard deviation above the mean. She's 0.8 standard deviations above the mean. Jackson, again, we know that his z-score should be about -2.5 because he's 2.5. Think about them being an outlier or an unusual point if they're outside this middle 95%. So if they are 2 standard deviations below the mean or more, or if they're 2 standard deviations above the mean or more, they're going to be an outlier. So think about the outlier range is here. So Jackson was certainly an outlier. Okay, that's the same thing, right, as saying they're going to be an outlier if their z-score is 2 or greater or -2. So Kia gets a 540 on the Math SAT score. Okay, but Jackson scores 380 on the Math SAT scores. So we would say yes about Jackson being unusual. Okay, so this picture, standard deviation that we're going to... Okay, so to be more precise, if we want to know if something's unusual, we just want to see how far is each score from the mean. We can be more precise about seeing how far from the mean we are. You can see below. We said if we calculate something called a z-score. And again, this is an important definition. You're going to use z-scores a lot, so you want to remember this. To calculate a z-score, we're going to take the score minus the mean and divide by standard deviation. So let's get Kia's score to begin with, the z-score. Remember, she scored 540. The mean score was 500, and the standard deviation is 50. When you put this into your calculator, be careful. You want to subtract first, hit enter, and then divide by 50. If you don't do that, you'll get an incorrect answer. We want to round z-scores to 2 decimal points. So Kia's z-score is 0.8, and the mean roughly. Let's get his value. So Jackson scored 380. If you work out this calculation, you'll get -2.4. So that seems reasonable based on what we talked about. He is about 2.5 standard deviations below the mean, or not. Okay, so how do we determine whether or not someone is an outlier? All right, and that's where this rule comes into play. Okay, so anybody who has a z-score of 2 or greater or -2 or smaller, we'll consider an outlier. But this rule only works if your data set was roughly mound-shaped, symmetric to begin with. So if your data set is skewed to the left or right, we cannot use this to determine if we have outliers. We need another way to do it. The other way to do it is to do this. We're just trying to assess here any data point. This is just a calculation. So we'll calculate this number. Any data point that is more than this number above the third quartile. Remember, the third quartile is the upper 25% of the data. If you're this far away from the upper quartile, we're going to consider you an outlier. Likewise, if you're this far below the lower quartile, we're going to consider you a small outlier. So let's try that. Here are some data, looked at the amount of cash that people had on them on a given day. We want to see if there's any outliers. So we're going to look for data points that are Q3 plus larger than this. 1.5 times the IQR above Q3. And then we're going to look at Q1 and we're going to subtract off 1.5 times IQR. Okay, so to get the IQR down below, I've already given you the 5-number summary. It's just Q3 minus Q1, which is 42.25. And 1.5 times that number, if you multiply it out, you get 63.375. Okay, so you want to add that to Q3, and then you want to subtract that from Q1. Okay, and so in the first case, if you add those two numbers together, you get 105.625. So any data point above that value will be an outlier, and I can clearly see I'm going to have some high outliers. 105 is roughly here. We've got data points above that. And then if we take Q1 and subtract off 63.75, we get negative 63.75. So any data value below that's an outlier, and we don't have any negative values here. So no low outliers, but definitely we have high outliers. I don't have all the data set here, so all I can tell from the picture, I knew the max was 500, and that certainly exceeds this. So I have at least one outlier. I can see from the picture I have more than one. These are all high outliers. In Minitab, you can make something called a modified box plot. Under where you go to box plot, if you go to options, you'll see an option for a modified box plot. And what that does is if there's any outliers in your data set, it's going to identify them with asterisks. So we can see in the data we were just looking at, there were 5 outliers. And what Minitab does, or any software does then, is a stop the high whisker is going to stop at the last data point that was not an outlier. All right, so here's the distribution of for our modified box plot for this cache data.